So today we're doing something a little different. We're not just looking at the universe, we are listening to it. We're tuning into the deepest, oldest, and most violent corners of space to decode these mysterious signals that are, believe it or not, telling us the life stories of long-dead giant stars. You know, this quote from Christopher Berry just nails it. It paints this incredible picture of astronomers as cosmic paleontologists. We're sifting through the fossilized remains of these celestial titans to piece together the history of, well, everything. Okay, so that sets up the big questions, right? What exactly are these cosmic fossils, and how in the world can we hear them? I mean, sound doesn't travel in space, so what's really going on here? Well, the answer starts with the message itself. To get how we can hear anything at all from these events, we first have to talk about what's carrying that sound. And that's something called gravitational waves. Think of them as the echoes of the universe's most dramatic moments. So, what are they? Okay, imagine space-time is like a giant, stretched-out trampoline. If you drop a bowling ball on it, it creates a dip, right? Now, what if you had two massive bowling balls spiraling into each other? They'd send out ripples across that whole trampoline. That's basically what massive objects like black holes do to the very fabric of space-time, and it's those tiny ripples that we can detect here on Earth. And this whole process creates what scientists call a cosmic chirp. It all starts with two absolute titans, like a pair of black holes or neutron stars, trapped in this kind of gravitational dance. They orbit each other, losing energy, spiraling closer and faster, until bam, they merge in this unbelievably violent collision. And that's the moment that sends these powerful gravitational waves rocketing across the cosmos at the speed of light. Okay, so where is all this cosmic drama happening? It's all going down in what astronomers have beautifully named the stellar graveyard. And yeah, it's pretty much exactly what it sounds like. It's where the universe's giant stars go to die. And this graveyard is filled with some seriously spooky residents. We're talking about the remains of stars that were at least 8 times bigger than our own sun. When these giants die, they collapse into either a black hole or this super dense object called a neutron star. And these stellar corpses, well, they don't always rest in peace. They can pair up and eventually merge, creating these different combinations you see here. And each one sings its own unique gravitational wave song. And here's the really cool part, the reason we call them fossils. By listening to these signals, we can actually reconstruct the life story of the stars that created them. It's like finding a dinosaur bone and being able to tell what it ate, how it lived, and where it roamed. It's the same idea, just on a cosmic scale. All right, and that brings us to right now, which is the really, really exciting part. You see, there's this global network of detectors, LIGO, Virgo, and Kagra, and they've just dropped a bombshell, a whole flood of new data. And what they found is just wow. Okay, get this. The headline number is 128. That's 128 new merger events detected in just the first 9 months of their latest observing run. To put that into perspective, that is more than they found in the first 2 observing runs combined. We're talking about an absolute treasure trove of new data to dig into. So you're probably asking, how did they do that? How did they suddenly find so many? Well, it all comes down to a massive upgrade. The detectors are now over 25% more sensitive. And that sensitivity boost means they can hear fainter whispers from much, much deeper in space, expanding the volume of the universe we can listen to. And buried inside all that new data was something extra special. 2 of them, actually. They found 2 new mixed mergers. That's where a black hole literally swallows a neutron star. Before this, we had only ever confirmed 1 of these for sure. So finding 2 more at once, that just tripled our entire catalog of these super rare events overnight. And as if that wasn't enough, they also caught this one signal, GW230814. This is the loudest, clearest gravitational wave signal ever recorded. Now, why does loud matter? Think of it like a crystal clear audio recording versus a fuzzy one full of static. A loud, clean signal lets us make incredibly precise measurements. We can use it to test Einstein's theories of gravity like never before. So let's just recap for a second. We have more signals, clearer signals, and rarer signals than ever before. But so what? What does all of this actually tell us about the universe? What fundamental questions can we now start to answer? Well, that's what's so amazing about this. This one fire hose of data, as they call it, helps us tackle some of the biggest questions in all of astronomy. How do these massive stars live and die? How do black holes get so big? Just how fast is the universe expanding? And maybe the biggest one of all, was Einstein actually right about everything? Let's just take one of those questions, the expansion of the universe. To measure that, you need a good ruler. And gravitational waves give us a brand new, ridiculously powerful cosmic ruler. The signal itself tells us almost exactly how far away the event happened. That's a huge deal, because measuring those kinds of distances is normally super complicated. This gives us a new, independent way to check our math on how fast everything is flying apart. But you know how it goes in science, right? Every answer you find just uncovers a bunch of new, even more interesting questions. And this latest batch of data has revealed a really juicy new puzzle. Okay, remember those two new mixed mergers we talked about? The ones where a black hole eats a neutron star? Well, an event that violent, ripping apart an entire star, that should create a massive flash of light, an explosion we can see with telescopes. But here's the thing, for both of these new events, astronomers looked and they saw nothing, just silence. The gravitational wave was there, but the flash of light was missing. So, where did it go? And that is the next great hunt. We have these amazing new observatories like the Vera Rubin telescope that are about to come online. They're designed to scan the entire sky way faster and deeper than anything we have now. The hope is that they'll be able to finally catch these faint, fleeting flashes so we can pair the sound of the wave with the sight of the explosion. It's pretty wild when you stop and think about it. In just a handful of years, we've gone from hearing the very first whisper of a gravitational wave to building this huge library of cosmic collisions. Each new signal is like another fossil, another piece of the puzzle. Our cosmic ears are getting sharper every single day, and it just makes you wonder, what secrets is the universe going to whisper to us next?